Good morning, everyone. Looks like we've got a few folks hopping online this morning. We've got a number of panelists with us today, so we'll give another 30 seconds or so before we go live here. Sometimes it takes us a little time to go between Microsoft Teams, Zoom, and any other type of webinar we're on these days. Excellent. Well, I think we'll go ahead and get started this morning. I will just welcome everybody to the Critical Canadian Building Science series. This is, I think, our 13th or 14th webinar series that we've done. And again, they're available online and we're supported by Enbridge and partners. The session today is on air barriers and multifamily low-rise housing, and we have some special guests with us here today. So before we get started though, folks, Enbridge has been a very good support to the builder community here in Ontario and otherwise. And Joanne has joined us today. Joanne, if you want to come online there.
Thanks, Andy. So we'd like to start today's session by acknowledging that the land on which we gather is the traditional and historical lands of the original people of Turtle Island, who have been the caretakers of these lands since time immemorial. Today, this gathering place is home to many First Nations, Métis, and Inuit peoples. Our acknowledgement of this reminds us that our great standard of living is directly related to the resources of and relationship to Indigenous peoples, and we have a responsibility to honor that.
Thanks, Joanne, very much. It's very nice.
So we just have a couple tips that we wanted to share with our participants today. It's always important to know who to call for help. Enbridge is a big company and sometimes it's not always clear who you contact. So we have two main contact numbers. One is specifically for builders and HVACs to discuss any questions relating to new gas service, projects, meter sets, final inspections, and our regular customer service care centers related to anything about cutoff at mains, forms, or billing issues, and damaged meters or safety violations. And speaking of damaged meters, we always like to include a quick little safety moment in all of our meetings. And I thought it was a good time just to kind of review what happens if you do damage a natural gas line or a natural gas meter. You know, we're all human, accidents do happen. So if this happens, we ask that you stop work immediately, clear everyone from the area, call 911 if you smell or hear gas escaping, and then you can call our Enbridge Gas emergency line, which is 1-866-763-5427, and then we'll get our teams dispatched to take care of that.
Awesome. Thank you, Joanne, so much. And thanks to the Enbridge team for supporting these Critical Canadian Building Science series. All right, we've got a packed agenda today, so we are going to move really quickly. We've got some polls, so get your Zoom fingers ready as well. Got the intro. We're going to give a little bit of context around compartmentalization, multifamily housing. Michal Bartko, Dr. Bartko has joined us from the NRC. He's going to be the heart of the presentation, and then hopefully at the end of the day, we're going to have a little time for some Q&A. So we're going to run a couple quick polls, though, just so we have a sense of who's online today. So look at the polls on your screen and tell us where you're from. And if you don't fit in one of the circles or buttons, then drop it in the chat. We'll give you about 20 seconds to let us know where your address is. I think we've had folks as far away as like South America and some European countries too recently. So Canadian building science is fascinating, really. So good, excellent. So that gives us a sense. We've got Ontario, British Columbia, Alberta, and potentially some other areas. The next thing we're going to ask you is what keeps you busy? Give us a sense of who you are, what do you do day to day? And again, if it's not in here, feel free to throw it into the chat. That is great. We often get a real cross sections from builders, developers, energy advisors, engineers, manufacturers, code officials. It's nice to have a nice cross section. We've got some student researchers too. That's great. Good to have you. So yeah, we've got a mix of everybody: architects, engineers, energy advisors, consultants, material reps, mechanical designers, and others. Beauty. All right, a couple housekeeping rules. Again, if you have questions for the presentations, we'll keep that to the end. As you have questions, though, feel free to put them in the Q&A. Please do not put them in the chat, put them in the Q&A. If you have technical questions related to the Zoom itself, are there recordings, all that kind of a thing, you can put that in the chat. Be considerate, be thoughtful, be respectful. I'll simply say be Canadian. And it's good to have good discussion, but also be respectful both in conversation and in chat with each of the colleagues on the team today. The admin team is in the background. Stacy is in the background as BKC webinar to commune with you in chat if you have questions. There is a survey that will come out as soon as the presentation is done. We would ask, please, if there's anything we can ask of you, please fill it out. These sessions are free. They're not charged for, thanks to Enbridge, but we do look for some feedback. That's our big ask. The links, the presentation materials, and the recording will be sent out to all attendees, so you can look at it later on. We'll move through some of the slides fairly quickly, but you'll have access to them later to get more in detail. And feel free to use the presentations. We have a lot of folks that use them with team meetings. They show them to team members. They watch them over the lunch hour. And also keep in mind that closed captioning has been enabled and is at your use. So we have a couple guests with us today. We have Frank Lohmann, Director of Building Science for the Canadian Home Builders. Frank's been in the industry for a number of years, works at Code Canada for a number of years. Michal, Bartko, sort of our guest speaker today, is a research officer at Natural Resources Canada and is the one doing the testing on some of these demising common walls. We have Mark Rosen. He's our own Director of Building Science here at Building Knowledge Canada. Mark's involved with a lot of the development of the building codes, doing some research. So we have Mark on today to sort of help us out. And of course, myself, Vice President here at Building Knowledge Canada. So I'm going to jump into a very quick presentation, and really the thing that we put before our presenters today, or sort of the idea, the concern we have in the industry, and this has been ongoing, is that are we really putting air barriers in the right walls when it comes to multifamily units? And the thing we need to understand is that traditionally the building codes in Canada have really only identified the air barrier around the outside of the building, and they have forgotten about that air barrier between the units. And so this is what this study is about. This is what the conversation is about. And the term that we often use for putting air barriers between suites inside of a building is a term that is very old, sort of identified during the construction of the Empire State Building. It's this term compartmentalization. And if you go back to the original, some of the original Building Science Digest, that was Handegord and Hutchin back in the day, Canadian IRC 2001, there was even some write-ups in that day about the benefits of compartmentalization. Just a little bit of historical context, there was also some early 2000 research done by CMHC that identified the benefits of air barriers between units in multifamily buildings. And it isn't just energy, it was also about health and optimizing mechanical systems. Another study that was done in 2005, 2006, and again, you can look this up, it was done by the Center for Energy and the Environment, CEE, is done by Finch and Hill, identified that it was, air tightness improves not just heating and cooling, but it's occupant comfort. It reduces odors. It gives the mechanicals the ability to actually work in a building, and the ventilation systems. The one thing we do need to understand, though, is if you ask any energy advisor across Canada today that is running these big red doors on multifamily units, and in the US where they're running blower doors as HERS raters, they will tell you that the air leakage, when you do a single point test on a middle unit, that about 30 to 40% of the air coming into the unit is coming from the neighboring suite. And that is when it is typically a 1 hour design, a 1 hour double stud offset design. Often in our industry, we've been told, well, you can do guarded testing. You can do multiple doors. So you depressurize the neighboring units and then you get a real test for that middle unit. The problem with guarded testing is it's very expensive. It's not easy to do. And the thing is, it's very minimized as far as can it be reproduced. You'll see here a study that was actually done in the state of Minnesota actually identified that you can see that the blue markers represent the guarded test. The red is the unguarded. So a big differential there. Another study you might want to look at that's been formative is a study that was done by the Department of Energy in the US. This identified both that, when we look at these townhomes, that there was tremendous leakage between units on middle units. They suggested that 50% of the leakage was coming from the neighboring units. They looked at that in developing the IEC C3 air change target and found out that a lot of the multifamily units, even in the US, couldn't even meet the 3 ACH, and that the typical results were more between 4 and 5 ACH. We now see programs to that point, like FIAS and others, instead of using ACH, they have moved to NLR, which is a different metric. And again, we'll leave this with you for you to look at later on. The study suggests why the move from ACH to NLR was important. Here's some baseline references as to what the air tightness standard is for multifamily. AT in here stands for attached units. And you'll see here that Net Zero Ready in Canada is 2 air change or the NLR equivalent, 3 air change or the NLR equivalent, and so on and so forth. And again, these slides are just for your reference. A little study done by the Owens Corning team a number of years ago showed that, hey, when you have holes in demising walls, it significantly impacts the sound transmission. Even a tiny crack can actually decrease the sound attenuation performance. Just so you know, one of the solutions to this in Canada over the last 10 years has been to put an air barrier material in this 1-hour assembly. And this is sort of a standard practice here. The only issue with this is there's nothing in the code to guide this. And there's often been the question, well, what if we add this spun bonded polyolefin to the assembly? What does it mean for the fire rating? So hopefully Michal Bartko, our guest here, can help us with that. The other one too that we see is we do see products like Aero Barrier that can help with compartmentalization and, get down into some of those low NLR, low ACH ranges. All right, I'm going to pass over to Frank Lohmann. Frank, if you want to give us a little bit of context from the point of the industry, the home building industry, and the Canadian home builders.
Yeah, I cannot share my screen, unfortunately. Oh, now I can. Okay, perfect, good. Yes, I will do that. Thank you, Andy. I'm hoping everyone can see my screen in this second. Okay.
There it is.
Thank you. Yeah, so just a few introductory words to what CHBA's role was in this research project that Michal is going to talk about. Apologies, my phone is speaking to me. As Andy just said, is in the code and in the energy discussion, the party walls really shouldn't matter because no heat is really lost to the adjacent units. But energy requirements do bring a lot of attention to wanting party walls airtight. And so this really opens the question. So then what is the problem we're solving? Andy spoke about the guided test being impractical and expensive. And the code, and we saw some examples of that, dealing with that by introducing different numbers for attached versus detached units, which suggests that they were inferior in performance, which they may not be, because this is just the effect of the adjacent party wall units contributing to that infiltration. And so, and he mentioned the safety and health implications as well. So this is but this is outside energy, of course. So it would be to build better practice party walls to really manage, for example, radon ingress or the risk of depressurization, to make them smoke tight, not just for indoor air quality irritants, but also for, who knows, cannabis, or maybe even smoke from fire. And you mentioned the air tightness as well. So all of those are really good reasons to build the party walls airtight. And what we found in about, I think it was 2020, Michal may correct me, is like if someone wanted to do it better and right, what is the best way? And we started looking, and Andy said, yeah, there isn't really much in the code. There's some stuff in the builder's manual, CHBA's builder manual. I'll show you a few snapshots in a second. And then there was, I guess, a difficulty with, offset exterior walls, meeting party walls. How do you detail that? And there are other construction process related difficulties sometimes, because if you have a multi-story attached units, there's often openings being left in the entire unit for trades to make it easier to pass from one unit to the next. and then they get left open until the end, and sometimes potentially those closings lead to some leakages. And as Andy said, there isn't much information in codes and not even in the illustrated guide. I'll show you just snapshots I took this morning from the CHBA Builder Manual. I'm not going to go through those in detail, but there's quite a few different, whether it's masonry, whether it's curved, whether it's offset walls, whether it's double stud. So quite a few things, and we really would like to update that. So in a nutshell, really, what's the problem? Well, the common part of all the problems that we just discussed possibly is that they deal with air leakage. But what's not known, or hasn't been verified until this point, is what actually constitutes to best practice. Is it fastener? Is it openings? And I'm hoping that Michal will talk to us about that. And so what was our need? Well, we wanted to really nail down what best practice is so that we can broadly communicate this, include it in our manual, and also communicate it to our members and others in the industry. And so our action was then at the beginning of this project to help NRC identify common and potentially best practice in the construction of these partition walls, and so that NRC could incorporate them into an evaluation or into a verification validation project. So our wish was that we will have validated evidence-based best practice in our manual. And with that, before I pass it to Michal, we wanted to run a couple of questions by you, because there's still open questions and we'd like to know what in the last 2 or 3 years may have changed. So I think it's Stacy or someone's running those polls. Thank you.
All right. Yeah, these are really good polls. So folks, if you want to take a minute, we're going to run you through about 6 questions real quick. They'd be very helpful. So.
And I believe I will stop sharing now. Yeah.
That's good. So do you always test or recommend testing units for air tightness? Stacy will let you make the decision when to move along, so that's good. Oh yeah, so 100% of the time, depending, folks say that they always test or recommend testing. Some depends on the project. Good. Move to the next question. And the next poll.
Hold on one sec, Andy. It's not
No problem.
here. Hold on. There we go.
Yeah, I think it's about the proven party details. Who's building buildings or is advising or consulting builds has a proven detail to go to for each of their products.
So the question is, do you have a detail right now, like a drawn detail that addresses air barriers and common walls? That's a good question. Interesting to see those. Yeah, so again, this will be very helpful to know. Interesting. Some do and some don't. It's almost split down the middle there, Frank. That's interesting.
Yeah, very interesting.
And the next poll.
Yeah, this is a follow-up to the if you have a party wall, a detail, does it involve a membrane type component? And
Okay.
then so we would want to know which one or what else you're using.
Yeah, whether it's poly or Tyvek or some sort of like spun bonded polyolefin or something, eh?
We should have expressed those in generic terms. You're right.
That's all right. Some of these terms are almost seem generic to the industry. So the answer is okay. So it looks
Good.
like it's a split, eh? Interesting. Poly, Tyvek, use a combination. That's good. All right, next question.
So the next question is about construction opening. I mentioned that earlier in the construction process. Sometimes there's little pieces left open until the end, and this is about whether you do that. I think there's one other question afterwards. Mm-hmm. So this is simple: yes, no. Do you have these construction openings when you build attached units?
I just want to note too, Frank and Michal and Mark, over in the chat, Zoran and some others have actually made some comments about what they're doing. So we'll collect those comments. That's good. It's good to know.
Oh,
okay.
Good.
Yeah, good.
Yeah. All so right. The last question then is, if you do, for those who do use those openings, do you have someone dedicated afterwards to be responsible for sealing that again to make sure that it's all airtight and matches the sealant and the airtightness of the existing party wall that
Mhm.
was not disturbed by construction opening. And then if so, who is it?
All right.
Good.
Yeah.
Okay, thank you so much.
Good. All right. Well, thank you, Frank, very much. That was very helpful. And again, folks, we'll get some results out there. Oh, there's the last one. Sorry, we did have one. Yeah.
Yeah, so this was, do you have callbacks for noise or indoor air quality? So there's an I missing, sorry, typo, I may have missed that. Indoor air quality, are there any effects of those that we mentioned, non-energy related, obviously, but that lead to callbacks? Noise probably the biggest one that we could add to our list of benefits of doing in this airtight.
And by the way, folks, when you do give answers, it is anonymous. So if you say you have issues, we can't actually track it back to who put the answer in. So, but yeah, just be open and honest about some of these things. We do know in general that since the requirement for air tightness and better air tightness in homes has occurred in the building code, that we have seen an increase in the warranty programs in sound and odor transfer concerns between units. So
this is interesting. Okay, so this is excellent data for us. Thank you. We can work with that going forward. Thank you so much, everyone.
Okay, Michal, welcome.
Good morning, good afternoon. Thank you. Thanks, and thanks, Frank. So let me share my screen as I hope you can see my presentation now.
We can see it very well.
Okay. My name is Michal Bartko, as I was already introduced by Andy. Thank you very much. I'm with National Research Council. And several years ago, we started working on a project defining airtightness of partition walls between adjoining residential units. This was originally, or this is a code-related project. We are supposed to provide the input data for future code change request and future proposal for including airtightness of partition walls between in the code. And as the project evolved, airtightness didn't remain the only issue that we addressed, but also we were asked in the phase 2, I will be describing in coming slides, that we should maybe also evaluate for specific assemblies, fire resistance and acoustic evaluation. Okay, so my presentation is going to consist of a brief introduction and background, why, what, how, and then I will be talking about phase 1, current industry status. In the first phase of the project, we collected, and I should say thanks to Frank and his team, we were able to collect some data where the industry stands today in terms of partition walls. And so we built up a specimen list, and then we tested them. And I will be talking about which specimens, how, which test procedure we selected, how we tested them, which facility we used. And then I will be presenting results of phase 1 and conclusions. And then phase number 2, future code requirements. After this phase 1 was evaluated, we made just a small break to evaluate, okay, so this is where we are today and what could bring us to better performance. And again, with help from CHBA membership, thank you, Frank, again very much. We will compile the list of test specimens for the phase 2, and I will or I will not share the results. The thing is that the project is still running. We are not completed with it, and we don't have the final recommendations. We should be having this in a couple of months, and I'll be more than happy to share the information with you once we have the project completed. All right, introduction. As already both gentlemen before me said, today's construction in Canada is more and more attached on multi-unit residentials. Either we are talking about high-rise and mid-rise multi-units per se, or low-rise row houses. And wall airtightness is becoming great concern because of the several results. I'm going to say that I am sure that nobody wants to, sitting in the living room, smell what the neighbor is cooking, or worse. So we do want the party walls or partition walls to be airtight. And I have this sentence here that the partition wall airtightness is not included in the National Building Code whatsoever at this point. And this question mark at the end, that should it be? It's apparent from the conversation before that it absolutely should be. We believe so. And also, as I believe it was Andy who mentioned that compartmentalization is great benefit, and airtight party walls definitely help with that. A little bit about background, how this project came about is that at the beginning of year 2020, 3 years ago and some, we approached our key stakeholder, Canadian Home Builders Association. And with their help, we were able to gather data from the CHBA membership, giving us the information, the input on where the industry stands, the first phase. Then we had we created small committee meeting. We had several meetings. We introduced the project. We asked the questions. We gathered the answers, and then by the end of year 2020, we had approved a list of specimens to be tested in phase 1. I'm not going to spend too much time on this slide because I will be talking about each and every specimen in more detail so that you are aware what we did in the phase 1. Maybe it's just enough to say here that we tested 6 specimens. Specimen number 1. The information, again, it's from the information extracted that from the input that we received, and we defined specimen number 1 as double wood stud wall with air barrier in between the studs. As you can see here, on each side we have drywall system, fire rated and regular. Then there is 2x4 wood stud filled with insulation, which is fiberglass insulation. In this case, it's not thermal, but acoustic. And then in between studs, there is 1 layer of 6mm poly sheet. This is attached to one of the studs, and actually the assembly is mirrored to the other side. Poly sheet has been attached to one side, and there has been 1-inch air cavity in the assembly, which was allowing the air barrier, the poly balloon a little bit. I'm a little bit giving away of the results. I'm not even saying that this is a good thing inherently, but this is how we built the specimen number 1. The specimen number 2. Again, this is related to the question that Frank had for you. Are you making those construction openings in the poly sheet? So here on the specimen on this right exploded diagram, you can see this vertical line, which was basically a 2-meter high vertical cut. We basically cut the poly and tested the specimen like that, unsealed. Again, we hear and we could see in maybe in the polls that these things happen on site. So to investigate the effect of such thing on air leakage was investigated. Specimen number 3 was similar. Again, it was again double wood stud 2x4 with identical drywall systems on both sides. The difference is that the poly sheet was not between the stud, and it was not one of them, but it was 2 of them on outer side of the wood studs. And again, in phase 1, we only tested 6 mil poly. And this was true according to the input that we got those three years ago. I don't know if I mentioned ever before that the specimen size was 2.4 by 2.4 meters for all the specimens, because this is the size of the facility that we have at NRC. And we also investigated the effect of openings or penetrations into the drywall system, as well as poly sheet in this case, with the electrical box installation and simulated exhaust fan simulation, penetration. Specimen number 4. There was a need back then that maybe we should address the effect of penetrations. You know, again, you are in your living room in your house, and you definitely want to put maybe some painting on picture or mirror on your party wall, and that causes some air leakage penetrations. So we installed 5 nails into the stud locations, so that they penetrated the air barrier poly sheet and were attached to the studs, and 5 pieces of screws with the nylon plugs, again going through the drywall and through the air barrier on both sides. Specimen number 5. It was believed that we should test party wall and floor connection detail. And on this slide, I am presenting adjustments that we had to make because our facility can only do 2-dimensional specimens. And the detail that on the left, and as I'm showing, is a 3D. It has it should be understood that this is the party wall of the lower floor. It's a vertical cross section detail. So it's the lower floor party wall, floor joist, and the top floor party wall. So we removed the floor joist, and basically just the rim boards remained in the specimen, which resulted in the following detail. Again, we used 2x4 wood stud with a 2 poly sheet air barrier on both sides, and then the poly sheet was actually interrupted and sealed for the bottom floor around the rim board, and again for the top floor. So we had 3 pieces of poly that were sealed together in 2 locations. Rim boards were 2x10, which we believed it was identical to what is being used in the construction commonly. Again, exploded diagram. This is just the repetition. This was basically prepared for our technical officers so that they know how to build the specimen with the dimensions. And here is adjustment or specimen number 6, which is a connection of exterior wall with the party wall. Again, 3D had to be adjusted to 2D. Basically, what we did is that we removed the portion, we shortened the party wall, we removed the section of the envelope, and we rotated the party wall into the one level. This is as close as we could get to the reality. Again, having the limitations of 2D testing assembly, testing facility only. And it resulted into this detail that on the envelope side on the left, we are using by 6 wood stud with a poly on the interior side and the Tyvek weather barrier on the outside. We ignored the air cavity and cladding. we didn't deem appropriate or important for a cladding to be included in this assembly. And again, on the party wall side, two wooden studs 2x4 with a poly sheet on both sides. And one important note here is that this detail here, connection between envelope and party wall, was not sealed. The poly sheets were not connected. We were going to initially run the test with poly unsealed versus sealed, but as we will be able to see from the results, it was not necessary because, again, I'm getting ahead of myself. The leakage of this wall was 0, and that was probably because the two drywall systems were mudded together as they would be on site. Again, this is the exploded diagram on the building envelope on the left and party wall on the right. Okay, so these were the specimens. And this is the facility that we have at the National Research Council. It is metal chamber, not too deep. It's maybe only 15 centimeters deep here on the right photo here. Airtight, and we can see hose and air inlet from the back, which is in this location here. This dispersion of air so that it's not focused on one area only, but it's spread regularly along the chamber. So then we install the specimen against the chamber, as we can see here, and via our vacuum or fan, whatever we call it, with the data acquisition system, computer, and pressure sensors system, we were able to put air inside or actually take the air outside. So the fan or the vacuum worked both directions. So we were able to introduce positive and negative pressures on all the specimens. I hope I didn't miss anything. I hope this makes sense. So let me continue to test procedure. There is no ASTM standard or any other standard specific for party wall testing. So we adopted what is available, and is ASTM E2357 standard test method for determining air leakage rate of air barrier assemblies. The standard says, and we follow this procedure, that each test must consist of at least 7 points in one test. 7 points being different pressure levels. So we were actually varying pressures from 25 pascals to 300 pascals, obtaining those 7 points in between 25, 50, 100, 150, 200, and so on. And we did 3 tests independently for each specimen. The diagram on the right actually shows that we have 3 tests there, and yeah, this is quite corresponding results. As you could see, all 3 tests were showing quite identical airflow rate. The airflow rate actually was calculated using this equation in red, using flow coefficient and flow exponent extracted from the test from the equations on the right, and leakage at 70 pascals was calculated for each specimen, and then these 3 values were then averaged. Recently, I got a couple of feedback that maybe value at 50 is better than 75. Well, my presentation is going to be about 75, but we have absolutely no problem, with all the results and all the equations here. We have no problem to produce data for 50 pascals. We might do that in the near future, depending on the feedback that we will get when we present these results to TOAD committee, actually, task force for airtightness of the SKI, Standing Committee for Energy Efficiency, already saw this first phase results. So once we present this final version, we can get back to 50 if necessary. I digressed. Coming back to the test results of phase one, I hope this is again clear and nicely visible. I try to make this small diagrams corresponding to what is being written here. That this one-time polyfeed in between had quite large leakage. I must say that I was a little bit surprised to see this, and also the difference between positive and negative pressures were considerable. And then coming back to it and thinking about it and seeing at the test results, raw data, we were able to determine that ballooning that I'm mentioning in the specimen was not really a good thing. The poly was stapled to the studs, and as the pressure of 300 pascals applied, positive pressure, and the air barrier 6 mil poly ballooned, these connections between or at the places of staples were just torn. That's an assumption. We didn't open the specimen just yet. We will do it, I'm assuming, in the near future, and then this assumption will be or will not be confirmed. I cannot tell you at this point.
Mm-hmm.
Specimen number 2, polyfeed with a 2 meter vertical construction opening, or just vertical cut. We can see again that the leakage is massive. Leakage was massive. Again, there is a little bit of difference between positive and negative, but this could be, well, there could be maybe some valving. And again, when the specimen is blown and opens, it leaks more, and then when it's sucked back, it kind of partially seals. So this could be probably the reason for actually most of the differences over here. Specimen number 3 is 2 polyfeed, 2 times polyfeed air barrier on both sides, and leakage here is quite nice. Then specimen number 4 with the nails and screws being installed in the roof, in the wall, sorry, in the both sides. Leakage increased slightly. And then we tested the wall and ceiling connection. We couldn't really identify where the leakage occurred in this specimen, but it is what it is. I mean, it was 0.72 liters per square meter per second for this type of detail connection of floor, ceiling, / party wall. And then, as already mentioned, party wall and exterior wall connection. To my surprise, leakage was 0, but here my explanation, my assumption is that since the drywall system has been mudded and has been made airtight, and we all know that the drywall system, unperformed drywall system is actually good air barrier by itself. So what happened here is that, yeah, the mud was still holding in place. There was no movement. There were no cracks. We got good airtight result. Maybe now when we test, if I took that specimen after 3 years and retest it, maybe with some cracks already, the result would be different. We didn't test that just yet. Okay, so I'm concluding phase 1. And actually I already did when I was showing the results that we were anticipating that the specimen 1 will have lower air leakage because there would be no penetrations. And in real life, most probably they even will not, because in real life, there is never 300 pascals pressure difference on each side. We get, I don't know, 10 pascals, 20, maybe if there is a stack effect. So the result might be a little bit skewed by this fact. Nevertheless, this is what we get, this is what we presented. Difference between positive and negative pressure tests could be due to valving or ballooning and or ballooning. And then specimen 3, air leakage was lower than the previous specimens. And again, we are assuming that since the air barrier, the 6 mil poly, was firmly between studs and insulation on one side and the drywall on the inside, there was no movement possible. The air leakage was much larger, much better, much smaller. Effect of nails and screws was there a little bit, but it was not significant. And again, as already said and explained, the specimen 6 was not leaking at all, to our surprise. Once all these tests were done at the beginning of year 22, so basically 2 years after the project came to be, we elaborated the interim report, we published the report, and we presented the results to, again, to that small committee of CHBA membership with the questions like, okay, so this is what we get here in the first phase, and what should we test? What should we experiment next, so that we get good input data for the future code change request? And at this point, actually, I already mentioned that this project was introduced to airtightness task group of the SKI committee. It was at this point where I talked to a gentleman at that task group. Some people here today, I believe that they were present at that task group meeting. And as a result of the discussion of the presentation and the input from the code committee and the CHBA membership, we compiled a list of specimens to be tested for the phase 2. Here, maybe I should say that it says future code requirements, but doesn't mean that these specimens will go to the code. We just believed at that time last year that if we test this, we have a good input data, and the code change request can be made, and whatever the task group or a standing committee decides will go to the code. This is still to be discussed on that level. Anyways, we defined several specimens to be tested in phase 2. Specimen number 1, actually, we had to take a step back after all those poly sheet, including membranes. We were like, okay, we didn't test a specimen with no membrane at all. And I'm not going to say that there was no air barrier, because drywall system is an air barrier by itself. It's maybe not as durable, whatever. So we took that step back and we tested the benchmark. So basically, we defined the specimen without any poly, without any Tyvek spun bonded polyolefin, anything. And then it was good input from membership again that specimens number 2 and 3 should be tested. Sealed versus unsealed spun bonded polyolefin used as an air barrier instead of poly sheet. So we defined 2 specimens with 2 layers of this membrane on both sides between the stud and the system, the drywall system. Also, one very good comment was about the specimen with screws and nails penetrations. Imagining the situation that one owner decides to move from that unit with party wall in it, And he takes his mirrors, his pictures, his paintings, removes the nails and screws, and leaves without sealing them. No mud, no toothpaste, no nothing. He leaves, and then the new tenant or new owner comes and doesn't do anything either. He just puts his paintings over those holes. So basically, that's specimen number 4. What happens to the air leakage when we remove those nails and screws from the wall and increase the perforations even more? So that was specimen number 4. Then specimen 5 to 8, as I already mentioned in my first slide, title slide, that there was suggestion that if this is new into the code and we are going to use span bonded polyolefin membrane, there is no acoustic and fire evaluation for those. So I just compiled this list, came to my superiors, decision-making people, and like, okay, people want to do this. Give me the money. And they did. Believe it or not, they did. So I'm going to talk about next steps chronologically. As a first step, fire test was done. I mean, our fire department was keen to test these new specimens, and I was able to proceed fairly quickly with them. And again, that group has its own facility. It's called NLC Wall Furnace Test Facility, and there is a standard procedure to run such tests. So here in the facility, you can see the gas pipes leading to burners evenly spread over the area of the specimen here in the inside of the chamber. And also what they have here is the camera, and they have 2 cameras on the side so that they can monitor what's going on in the chamber, because it's, of course, it's sealed, it's tight, and we cannot see anything. We cannot see the fire from the outside, of course. So again, those specimens 2 and 3 from the previous list were built. The size is different. We used 8 by 8 feet for air leakage. The facility for the fire evaluation has different sizes of the specimen. It was 3 by 3.6 meters, but the assembly was identical. And also, I had a specialist to calculate load bearing of that wall. So it was tested under this 96.3 kilonewton load from the top. I am including some photos of specimen building. We can see double studs here with fiberglass insulation, and then stage where spun bonded polyolefin has been put to the place with drywall system, and then specimen was, according to the previous dimension standard, was instrumented with temperature sensors in this array, and also with displacement sensors. Since the system on the top here was putting the load, it was expected that at some point the specimen will crack, will collapse, and the displacement sensors were used for that exact purpose, like to see where and how much, what comes first. Okay, it was fun, let me tell you. Experiencing this test was really exciting thing for me. I've never seen anything like that, and I'm showing you the results already. You can see the cracks here of the displacement and the collapse of the specimen is visible here. And when the chamber opened, we saw the other side of the specimen exposed to the fire. I was surprised to see all the studs gone, and still periphery frame could still hold some of that load till it crushed, of course. And then the detail of the electrical plug on the side that was unexposed to the fire. You can see some smoke coming through and making its marks, but test was interrupted as soon as these cracks, this collapse of the specimen occurred, which happened after 75 minutes versus 72 minutes for sealed versus unsealed spun bonded polyolefin airberry respectively. What I mean here by sealed and unsealed is that for unsealed, we used staples only at the whole area. For the sealed, we had acoustical sealant at the periphery, and the penetration, the electrical box was taped up. So there was no air movement. It gave us 3 more minutes. I was quite pleased with these results, and I hope that you are too.
Yeah, that is very interesting.
Shall this make its way to the code at some point?
Mhm.
Okay, acoustic evaluation. We have acoustic group here. I'm not an expert, so what I'm going to tell you on this slide is just what I was told by my colleagues that did the test. There were 2 standards. One is for definition of sound transmission class, STC. Basically, how well the wall can absorb or attenuate the sound transmission. And there's another standard, this E9009, for defining the procedure, how this should be measured. So at the NRC sound transmission wall facility, I don't have a picture because it's actually a building. It's 2 chambers, really large, 250 cubic meters and 140 cubic meters next to one another with a spot with this red square comes. That's where the specimen is being put, and will be slided into that facility. And then one chamber is a noise source, and another chamber is a noise absorber, and basically these noise levels are being monitored. Various noise levels, I should say, are being monitored on both sides of that wall assembly. Again, sealed versus unsealed spun bonded polyolefin membrane was used, and specimen size. It's actually unfortunate, I must say, that each facility has different specimen size here at NRC. So we had 12 by 10 for fire, and we have 12 by 8 for acoustic. So here is the red frame that I showed you on that diagram, and here is the building, the specimen being built directly into it. You can see on the bottom that there are some wheels, there's some mechanism that makes this red square mobile. So basically, you build the specimen outside of that test facility on top of insulation, some membrane and drywall came. So this is the final specimen in that frame, and one more photo where the frame was slided in between, and I am inside one of those chambers taking this photo. Of course, during the test, you don't want to stay in. It's really noisy. It's a very strict test protocol. So basically, what happens? I do the photo. They drag me out. They lock the door. They take me upstairs, and they run the test. And from this control room, we are hearing noises, or louder ones, less loud ones, and high pitch and lower pitch. And here are the results. Again, the open air, unsealed air is affecting a little bit the performance, the acoustical performance. So that the sealed, or the lower air leakage is just better for all purposes here. Okay, and I'm coming slowly but surely to the end of my presentation. After these 2 parameters were evaluated. We built our specimen for air leakage. I'm not going to spend so much time on this slide. We have seen this a couple times. This is the procedure, how we built it. You can see staggered heads, unsealed spunbond polyolefin membrane, and the finalized specimen. Results. Okay, this slide is definitely to be completed, and I'm not going to elaborate on it. It's just that it's too preliminary. We have still several specimens to complete the test.
Mhm.
So conclusions are also not to be made at this point. It is to be completed in the near future. But what I can tell you, what the next steps are, is that in coming 2.5 months, we hope to complete all the testing. Then I will be elaborating and publishing the final report for this project, including all the information, all the project, all 3+ years of it. And then the results will be published or presented to the airtightness task group. And I believe that from that point on, I will be a member of the task group, so that we will be able to develop the code change request and collaborate with the task group from now on. And of course, being scientists, we will publish the results in journals and conferences. Thank you very much for your attention.
Thank you, Michal, very much. That was a very detailed update, and I know you folks have been working on this for a couple of years now. So we do have some questions. I see that Mark has been answering some questions in the Q&A. Let me just bring up real quick, just a sort of just the fact that we are right now at Q&A. Hold on a minute here. So let's take a little bit of time and let's answer some of these questions if we can. So I just want to go back and sort of restate what I think Michal has just told us. One is that we know now for approximately, I'm going to say almost 10 years, that a lot of builders and constructors in Canada, when you do multi-family units, attached townhomes or otherwise, and you have to test them with a blower door for either program compliance with Energy Star, net zero, R2000, LEED, you name it, or to satisfy performance, on code, that they have found that the common wall does leak, and that for about 10 years, they have been doing various solutions. And the solution that you're testing is a solution that I'm going to say, the royal we, Mark, myself, other energy advisors in the field often see used on a 1 hour. Now, when you go to a 2-hour separation, obviously you get into 8-inch concrete masonry, and that's a different conversation. So this is very specific to no 1 hour type of walls. Often that the product that they use as a air barrier in the 1 hour wall has been a spun bonded polyolefin. It could have been Tyvek, it could have been Typar, it could be something else, but often that is the product they use. It often is polyethylene, and you folks have tried that too. The question always has been, and this is what you're trying to answer or looking to answer, is how does putting some of these materials inside that assembly affect the fire and sound? And it appears, tell me if I'm wrong, Michal, that it looks like there's a negligible impact on, let's say, flame spread on the fire rating with spun bonded polyolefin, and possibly a favorable impact on sound attenuation. Is that sort of where this is headed, do you think?
I am going to agree on this, yes, and yeah.
Okay.
Not that I have extensive knowledge about other assemblies fire resistance, but from the discussions we had during the test with the researchers in fire lab, they were pleasantly surprised with this, and the fire resistance was not lower than other party wall assemblies that they tested before.
And this is good to know because, again, as Frank said earlier on, and some of the things Mark is working on with the building codes, is that the code is silent at this point when it comes to air barriers in these common walls. So in the absence of doing something in the industry trying to respond to issues, you know, we put the spun bonded polyethylene, we put the polyethylene in there. And this sort of helps us feel like, okay, we are answering, the solution seems to be okay, at least for now. Anyways, Frank, you've got your hand up there.
Yeah, I wanted to contribute to that acoustics discussion, because it is in fact a bit surprising. I think there was a question about that too, that the walls come in at an STC 51. I just wanted to brief everyone that the code requirements have been changed and that there is now an ASTC requirement, which means that all the exterior flanking walls and all the floors flanking contribute to potential flanking losses. But the fact that the separating wall between the units is an STC 51 means it can be used as an element in that, and it's not lower. There was one with STC 49, I think, that came in. That may not be enough, or you have to do a lot on the junctions between the floors and the walls because essentially it isn't just airborne sound, which we address with air leakage. It is also structure-borne sound, which gets reverberated on the floor on the other side and on the wall on the other side as airborne sound. Different topic, different webinar, but I think what you said, Andy, is correct, that these results are promising, and the construction practices that you used and evaluated should be added as specifications to the tables 9, 10, 3, 1, which are the fire and sound resistance tables that architects, builders, and everyone uses frequently to select separating walls and floors. And so if it was mentioned in there, because there's pictures and then there's a specific details listed, if it was mentioned that there is a membrane permitted, and it reaches the same, say, minimum 1 hour fire separating or STC 51s, that would really help the industry say, okay, well, and the discussions between building officials and builders, no, look here in table A91031, it says I can put a membrane in there without any detrimental effect. I think it's a major win here. And then I would like to see, of course, the practices being described in much more detail in the illustrated guides as it currently is. And as I said earlier, we'll do the same for part 9 for the CHBA builder's manual and the renovators manual. So I think it's really promising. Thank you.
Yeah, thanks, Frank. No, that's a good comment. Robert actually had a comment in there. He said, I thought the STC would be lower. Just wondered, did anyone else surprised at that? And I think what we sort of notionally know from building science is that when you, regardless of how good the mass of the wall is or the flanking reduced, is that if you still have air movement, sound energy can be carried on the back of air. And so if we take care of the air tightness, we see better STC scores. So those things you sort of know intuitively, but until you test it, you go, oh, I think it does. So that's good. There was a note there, Saki, just a note you made there, and I'm not real clear on this. So if you can clarify that, just saying this article may help better understand using Tyvek on interior walls. The manufacturer DuPont does not recommend it on interior walls. So that'll be an interesting article to look at. Again, whether it's Tyvek, whether it's Typar, spun bonded polyolefin, it'd be very interesting to look into the article and why it is. So there you go, Michal, Frank, and team. We'll have to look into that. And it is good that the product manufacturers know that their materials are being used, because this is either a market opportunity or maybe a need to do more research on it, is really what we're looking at. I do want to, there was a question there, Mark said, Mark, any thoughts on measuring the transfer of pollutants? I don't know whether that's for Mark or whether that's for Michal. Michal, maybe you want to, or you could both take it on if you want.
Measuring pollutants. Well, it would definitely be possible with some kind of sensors that we could attach on one side of our facility. I'm not going to speculate. We have not done this, or our group has not done this. Maybe indoor air quality group has. again, it's different group of people, and definitely the experiments are being done. I'm just not certain if the pollutants crossing the wall assembly as we speak, as the topic is today. I would have to confirm. Yeah,
that's okay. No, thanks, Michal. Mark, maybe you want to speak to this. I know this may be more of a response from the perspective of programs like LEAD requiring compartmentalization, because in those cases, it's not being specified for energy. It was, in fact, it was that good old tobacco smoke credit, right? That you wanted to compartmentalize.
Yeah, that's right. And as Kyle put into the Q&A and into the chat, compartmentalization in those standards is talked about using the NLR metric, which is a normalized metric by surface area, as opposed to ACH, which is more referring to the volumetric change of air in the space. And so using a metric like NLR to describe compartmentalization allows it to be equally applied to the party wall and the exterior wall and define an overall air tightness of the zone that you're testing, for exactly those reasons that you brought up, Andy, that Lee was concerned about the transmittance of pollutants when they define this, and other programs since then have adopted that metric when they're talking about compartmentalization requirements.
Yeah. Now, Mark, that's a good segue, because I do want to, let's talk about this. So we're testing common walls for air leakage. And most of the conversation today has been around, it reduces sound and odor transfer. But I want to go back to something that Frank alluded to, is that a lot of the reason we are actually blower door testing units these days is it's an energy metric. And the reality is when it's between a unit, is it really any energy loss, right, between units? But again, we're also finding, if you look at the earlier slides, that our assumptions in the past about how tight multifamily units are have been incredibly off. And we're finding that when you try to achieve, ACH of 3 or 2 or 1.5 in a multifamily, the leakage through the common assembly is hugely detrimental. And maybe it's not only about sealing the wall, but maybe it's about, maybe we don't want to use ACH anymore. And so can you speak to that? Where, is that being talked about nationally?
Yeah, it's a really hot topic, I think, and there is actually a proposed change that is in front of the Standing Committee on Energy Efficiency that we may see in public review in the winter, so keep an eye out for that. That suggests that NLR be the guiding metric when we're talking about air tightness levels in the code, as opposed to ACH. And the fundamental reason why this is, I think, a positive change is that NLR, or normalized leakage rate, is just that. It's a normalized metric, which means that you can say that a home A that has an NLR of, let's say, 0.2 and a home B of a very different size, but the same NLR, have assembly leakage that is equivalent. Whereas if you took the same two examples, one small house and one big house, and said that they had the same ACH value, they actually have very different envelope leakage rates. The small home would, in that case, be substantially tighter in its envelope assembly than the larger home. And this creates a challenge for attached homes in particular that tend to be smaller and that also tend to have, because of the unguarded blower door tests that are performed on them, the leakage through the party wall lumped in with the leakage from the exterior and applied to their energy models in comparison with the reference house, which can be a challenge for compliance in these homes, especially when you're talking about a metric that is, I wouldn't say incompatible, but is maybe not the most representative metric for that housing type.
Yeah. And that's also supported what you're working on at the NRC with some of those task groups you're on, you and Frank, for future codes, looking again at NLR as opposed to ACH for multifamily. You're sort of headed down the same direction. I think we saw even the DOE studies, in those earlier slides where you had, folks like, FIAS, Passive House, DOE, and a number of others, the Building Science Corporation, Stephen Winter and Associates said, hey, maybe it's time on multifamily just to leave ACH alone, move to NLR. What I found fascinating is they were identifying, benchmarking the NLR for multifamily in FIAS, Passive House, as being 0.3. And I just want to bring that to our attention, because right now in the Energy Star program in Canada, the benchmark is actually less than the FIA standard is. It's 0.26.
It's actually
again-
0.23, I believe, in the latest iteration.
Right.
So it's even creeping down. And that is the value that the national code has adopted out of the gates, is the 0.23 equivalent. In metric, that's expressed as 1.17 liters per second per meter squared. I'm still trying to wrap my head around the imperial versus metric numbers for NLR.
Yeah.
But yeah, it is quite a bit lower than what FIAS and LEED have both identified as targets for compartmentalization for their programs.
And I think that's where we have to be careful, is that we have these numbers. We have builders in Canada that have been able to do the NLR 0.26 on multifamily. It was dropped to 0.23 for some alignment purposes, but we still don't have good scientific, I would say, is my opinion. I've not seen good studies like what we're seeing here, or other studies to justify even 0.26 as a benchmark for multifamily. I think it seems like a lot of the times the data we're seeing is actually suggesting that's incredibly tight, like really tight, and maybe it needs to be less than that. And again, I'll just throw that out there, Mark. I don't know if you or Frank want to give an opinion on that, or...
I'll give a short opinion on that, and that is to say that the only studies that we have seen on this, or that I have seen, are usually dealing with very small sample sets. And the challenge there is that to get a good sample set that provides useful data, you need to be able to perform guarded testing and unguarded testing on the same units. And as we've already talked about today, guarded testing is extremely challenging, expensive, and incompatible with construction schedules at large. So we just don't have the opportunity to do it. And therefore our data sets are either small or imperfect. But that being said, some of the data that you showed on screen today and other data that I've been a part of collecting myself has shown that there is just a dramatic variety in how leaky the attached surfaces of units really are and how much they contribute. And playing into that, something that we don't talk about often enough, in my opinion, is that attached homes come in a wide variety of configurations. And there may be, a house that is only 6% attached to its neighbor and an apartment that is 80% attached to its neighbors, and they're both lumped into the same category of attached. Yet you might expect that one would have a much bigger contribution of leakage through the party walls than the other. So it's a complicated topic. That's part of the reason we have small data sets and imperfect information to use in these analyses. It's certainly a hurdle that we're going to have to keep trying to get over.
Yeah, Frank.
Yeah, I had one more slide to share, but I guess you still have your screen up because yes, it's. Let me just quickly share that here. Mark mentioned the proposed change form. I hope everyone can see it now. So it is PCF 1819, and much of the discussion, Mark is definitely the expert on all of this, and thanks for explaining that. I wouldn't have been able to do that even if I had brought the slide up without you. So much of this discussion is coming up during one of the public reviews. I'm not sure exactly which one is going to. There's one November, December 2023, and there's one in February, March 2024, or until April. Exact dates I couldn't find today. But for anyone who's interested in this and who has suggestions, or some of the metrics we just discussed as to being too stringent and needed to be adjusted, or what other programs are doing, because alignment of code requirements is really important. If you do get incentives from a program and you comply with that program and you have to do something different for codes, that's incredibly complicated. Why not use it? So that's what I wanted to say. And I'm hoping that the research that Michal did will not lead to, let's say, new requirements that make things more stringent. I'm really hoping that they will enable and permit the industry to do what they're already doing and get some credit for stuff. And I think this PCF has that potential to make it a fairer treatment, if you want, and a better consideration of the shared walls between attached units. So those are my hopes. That's what I had here, and just a public service announcement for anyone who's interested. Mark down PCF 1819 and look at the public reviews from NRC.
Yeah. Good. Frank, I do want to make a comment here. Saki sent through a link and I checked the article. So Saki, just to be clear, when Tyvek and DuPont are actually talking about interior walls in that article, if you go and read it, it's actually talking about interior walls between two rooms. It's not talking about a demising wall between two residences. So it's a very, very different scenario. So I want to just be a little careful because it could be a little misleading, because what we're talking today is not about interior walls. We're talking about exterior demising walls between units. So even when you read around that comment by Tyvek DuPont, it really is talking about interior wall type settings. So anyways, maybe at some point in time, we'll follow up with some of these manufacturers and give them a chance to chat. So very good. We did have, let me just see here. We had one other question I thought was really good. Michal, Rick Grattan, actually, Rick has been former, I think, chair of CHBA TRC. He's been a large member of the Canadian home builders community. Rick asked, are there any plans to do any testing like this for floor assemblies? You know, unit over unit, or right now is it simply vertical assembly demising walls?
Very good question. There could always be a phase 3 to it. If there is a need, I'm sure that our team will be more than happy to proceed with floor testing. Has there been talk about floor testing? No, not so far. But if there is a need to address this point, I'm sure that NRC team will be happy to work on this.
And if I may add, then the floor discussion, stacked units will likely include structure-borne sound, which NRC is equipped to test as well. And I think in that case, the test facility for sound and fire are actually in the same facility. So you're getting a benefit there, Michal. But that's a different sound that's not even addressed in the building code, because it's not just the airborne sound from the bottom unit to go up and vice versa. It's actually also the structure-borne sound, moving chairs and tables, running. And so they're currently not addressed in the building code. So that would be a best practice. Although if you look in the tables 8, 10, 9, 3, 1, or not A anymore, they're tables 9, 10, 3, 1, fire and sound, you do find impact sound ratings. And so it would actually be another enabling testing and evaluation, if you want, of floors. And when we can certainly help in doing the same thing we did for the phase 1 to establish what are current floor and separating assemblies construction practices. So that's possible good next step. Thank you.
Oh, it's interesting. Mark?
Yep.
Yeah, and in thinking about the floors and walls in this testing that Michal is showing us, I thought the one thing was really interesting, interestingly highlighted when you observe the ballooning damage that happened with that poly that was sandwiched in the middle of the wall, as opposed to the poly that was supported by the drywall clamping on either side.
Mm-hmm.
Really highlights the importance of supporting membranes, whether it's in a floor or a wall, whether it's behind a mechanical chase or in something like that, to prevent that membrane from over time releasing without its own support. I think just as we've known in exterior walls for a long time, you can't just rely on an acoustic sealant or a tape to do that. That mechanical clamping using drywall or a backing material has, I think, shown itself in the study to be very important, even in situations where you're not subjecting the wall to 300 Pascal pressure difference. And I just thought that result really highlighted that nicely in the presentation related to the question on floors. So I wanted to bring that up as well.
Thanks, Mark. Yes, I agree.
Yeah, it's interesting, isn't it? When you go back to first principles on building science and the definition of an air barrier, even in the building code, speaks to the air barrier not only being continuous and sealed, but also being rigidly reinforced. And so, yeah, that's a really good point, Mark. I think we have sort of closed out the questions. We've had some good comments there. Paul made a comment about, even exterior testing, guarded testing. So folks, I do want to thank everybody for your participation today. We are going to make this available because I know there was a lot of information shared. Frank's presentations, Michal's presentation, my brief few starting slides will be shared as well. Please feel free to reach out to Frank at CHBA, Director of Building Science. Frank is always looking for help from the builder community to be involved volunteers to help in the development of codes or to provide practical feedback. Because remember, the solutions, what I still find interesting about this is what Michal and team are testing are solutions that the builder community had to develop themselves because there was no guidance. And we're developing some things that are sort of useful. So in this case, it's the code catching up, right? Builders taking care of unintended consequences, because that does happen, but the code trying to catch up. So that's really interesting. So I'm going to just quickly wrap this up. Mark, Michal, Frank, thank you so very much for joining us today. For the rest of you, just know we do have more series coming up. We've got, I think, about 7 more critical Canadian building science series coming up. We have a 3-part series that I have on the screen that you're welcome to register for. This is a 3-part series that's going to touch on various aspects of the new Ontario harmonization of the National Building Code 2020. Again, this is set for August and September. Obviously, sign up when you can. I will just say that this may be bumped out a little bit depending on when the province does initiate or release that. But we have another session coming up on large building airtightness testing. We also have another one coming up on wood, impacts of new codes and climate resilience in the National Building Codes and the impact on structure. We're going to be having Robert Jonkman from the CWC and Corey McCambridge from the EAPA will be joining us, and I believe that's in October. So thank you again, folks, very much. Make sure you sign up. This is just a cheesy plug for our Building Science Digest newsletter. It comes out about once every 3 months. It's got lots of good stuff in there to look at for residential home builders. And again, on behalf of Enbridge, Building Knowledge, CHBA, and NRC, thank you very much for attending today. And folks, please enjoy the rest of your Thursday. Take care.
Thank you.
Thank you, Andy. Thank you, Michal.